Today, we have folks that have been with us before, so they feel like members of the family. In fact, Matt Segall is the person who is chairperson of the science advisory team of the Cobb Institute. Tim Eastman has a PhD in space physics. He was co-editor of that book on physics and Whitehead that was published in the SUNY series in Constructive Postmodern Thought. And his most recent book, Untying the Gordian Knot, published in 2020, prompted a whole series of 9 conversations that was sponsored by the Cobb Institute Science Advisory Team. And Matt Segall has assembled those in a place. You can also get them on our website. But Matt introduced them as a seminar on his own website. And Matt has reviewed this book, Untying the Gordian Knot. You can find that on Matt Segall's website. David Segall is the assistant professor in the Philosophy and Religion Department at the School of Consciousness and Transformation at the California Institute of Integral Studies. He received his doctoral degree there in 2016 in their Philosophy, Cosmology, and Consciousness program. So their topic today is my very untechnical phrasing of what is probably a highly technical conversation. I've just picked up on some of John Cobb's concerns about people who assume the Big Bang and multiple universes and don't give it a second thought. They just assume these are a done deal. And so my question is, how do scientists know? John, we'd like to give you a chance to add anything further that you'd like to do to introduce and welcome Tim Eastman and Matt Segall.
Well, I'm delighted they're here, and both of them, they're my 2 favorite teachers, and I certainly need a lot of teaching in the fields in which they have so much more knowledge and expertise than I. And it was Tim who first made me aware that there are alternatives, or at least is an alternative to this, to the dominant theory, and I've been very interested in that alternative, and I'm just eager to hear more about it today. So thanks to both of you.
Thanks, John. Thanks, Ron. Thanks to the Cobb Institute. It's great to be joining forces with you again today, Tim. It was great fun and a tremendous learning experience to MC a series of seminar conversations about your recent book, Untying the Gordian Knot. I enjoyed reviewing it, and Process Studies was kind enough to publish a review that's somewhat longer than what normal book reviews are. I couldn't contain my excitement and went on a bit longer than I probably should have for a book review, but folks can find that in the latest issue of Process Studies. Today, we're going to talk a bit about the Big Bang and alternatives to the Big Bang. Tim is going to start us off here with a presentation about some of the technical details, the problems with the so-called standard model of cosmology, and some of the recent findings from the James Webb Space Telescope, and some alternative proposals for how to interpret these more recent observations. And then when Tim is finished, I'll offer some more philosophical remarks about the rise of modern science during the 17th century and the bifurcation of nature which resulted, and how when we engage in the study of the universe as a whole or in cosmology, it might be important for us to revisit that bifurcation to see what other approaches to cosmology might be possible when we don't separate our own human consciousness from that which we are observing. So Tim, I'll turn it over to you, and I believe Richard's going to help us out in the background with your presentation.
Okay, well, thank you very much. for your introduction. And also thank you, Matt, for your excellent review in process studies. I had no control over it whatsoever, and you most independently did a very excellent review. I very much appreciate it. So I recommend people with their process studies issue in hand to look at that review and also at your site. So we had some technical difficulties with me setting up the presentation from my end. So I think we could proceed with initiating it. So what I put together is a adjustment of a prior PowerPoint I had done some years ago, but then updating it and giving it a new title and so forth. And here, associating it here with this current Cobb and Friends presentation of November 15th. My background is in space plasma physics as applied to the low density space medium, space environments, in particular, how the sun and the solar wind and the plasma is coming out in every direction from the sun at all times, then interacts with planetary environments like the Earth and creating a magnetosphere with a Earth's magnetosphere compressed on the sunward side, drawing out a long magnetotail, and how the effects of this, the dynamics of it are dominated by electromagnetism and plasmas, which I will get into more in this presentation. So we really have a situation of, for understanding various systems, some more dominated by electromagnetism and plasma dynamics, and some more dominated by gravity, such as the dynamics of planetary bodies. And it depends on particular application, which is the one you emphasize. So I call in general my overall framing of this a creative cosmos approach and understanding. Next slide. And back in 2008, I published a paper called Our Cosmos from Substance to Process in the World Future Journal. And in that, I distinguished the evolution of the basic physics from the Newtonian conception prior to 1900, for some couple hundred years. During that period of time, the Newtonian physical framework, which was exceedingly productive and led to much of important technological breakthroughs. So in that sense, as a very good approximation, it's well-founded. But then we realized with the advent of quantum physics and relativity theory, new developments that then constituted modern physics that I here describe as starting out in the time frame of the 20th century, 1900 to 2000. So that's on the physics framing. And then along with that are certain presuppositions, certain philosophic assumptions that tend to go along with these. And along with the classical physics framing was often a substance metaphysics, a classical Newtonian metaphysics of a certain kind, thinking of the world as a multiplicity of separate things in disjunction that then you could then take the particle description and effectively treat all dynamics in terms of those fundamental mapping down to a particle level, and just that aggregates are simply combinations of those. And so the basic metaphysics was substance oriented. So in the process tradition, we've really had a most systematic critique over the last 100 years from Peirce and Whitehead and others systematically throughout this last century, providing ever better critique of that kind of metaphysical presupposition, leading by late century to very good formulations of a alternative understanding in terms of a process, relational, or event metaphysics. And if one, so to speak, combines the basic physics with the metaphysical presuppositions, then one can think of that as the philosophy of nature, or that the combination is like a worldview of certain integrative approach. And the classical view was that combination of classical physics and substance metaphysics, which is basically the corpuscular kinetic worldview that Millichap critiqued, the say reductive, mechanistic, and materialist description. That's the classical view. And in the philosophy of nature line here in the bottom center, then the standard view is, so to speak, updating that view to one which is utilizing the new modern physics, but still holding on to the older metaphysics. And the combination of the modern physics with that earlier metaphysics, I think, leads one into this standard view, which has in turn influenced lots of things, even up until recent times. And I think in a way, the Big Bang paradigm, its research program is very much dominated by this kind of standard view with respect to philosophy of nature. Now, what we need is a movement onto a process relational view that integrates modern physics with the event metaphysics that has been so well developed in our community. Next slide. Yes, so I put together, so to speak, a list of characteristics of my particular, maybe somewhat idiosyncratic creative cosmos or process approach, and compared it with characteristics of the standard view, the Big Bang approach, or the Big Bang paradigm. Now here, again, as Matt will bring out later, a distinction between the research, the paradigm, the research program, and a particular quantifiable, testable component of it. So there's a distinction in Big Bang between the overall approach, which I'm addressing here, and a particular testable model. So in terms of the creative cosmos, I think in terms of that, it's, that's data-driven, observational inductive in terms of the framework of science. The Big Bang approach tends to be theory-driven and tends to be hypothetical deductive in terms of its methodology. On the one hand, the creative cosmos, I would say I would focus on a variety of possibilities for non-expansion redshift. The Big Bang approach basically assumes that redshift is essentially only a space-time expansion type redshift. And we'll come back to that. And then in this, my approach, I think in terms of the galactic origin of all elements associated with the nucleosynthesis model of Burbage, Hoyle, and others in 1957, that it's standard understanding that that's the dominant approach, nucleosynthesis, for the production of all elements except for the light elements. And in the Big Bang model, then there's some light elements, deuterium, lithium, and helium in particular, as light elements that are thought to be originating in the initial Big Bang event, and basically stamped with a certain abundance upon that event. But in the my creative cosmos approach, and like a particular non-Big Bang model, one can think that that there's enough time scale so that the nucleosynthesis approach of the work of Burbage and Hoyle and others can basically create all elements without exception. We don't need to have some additional way to, or a special way to originate the light elements like lithium. And also that I think in terms of the space-time metric, which is central to Einstein's general theory of relativity, if one can take that maybe as a fundamental notion, within the research program, to insist that space-time metric, space-time description, is fundamental. Whereas I think that quantum process is truly the most fundamental thing, and that space-time metric is derivative. Nevertheless, there's a certain fundamentality to the concept of extension, as argued by Randy Akshay in his fine book with Gary Erskine. I think they're right on there, but that's at the metaphysical level of description. But in terms of the particular physics of things, I don't think we need to commit to space-time metric as a fundamental entity. Also, I would caution people working in this area to avoid any dependence on the specific gravity model. And the standard model has exclusively depended upon Einstein general theory of relativity, pretty much, with few exceptions. And then I tend to think of the universe as inhomogeneous, anisotropic, and multi-scale without apparent limit, without any particular limit. The the nominal time back to the initial Big Bang event. I just set that aside and think that there probably isn't such a time limit. And that in the Big Bang model tends to assume that the universe, at least its initial way of framing it, was homogeneous and isotropic, and to develop inhomogeneities required certain types of evolution. And okay, next slide. So an additional set of characteristics I have in the next slide. So the standard approach tends to neglect plasma processes at all levels, focusing on gravity as the only effective long-range force, and presuming that plasmas and electromagnetic effects are always fully shielded. Well, in contrast to that, I insist that there's two long-range forces that we need to attend to: gravity and electromagnetism. Gravity sets the stage, but plasma can be dynamically important at multiple levels, and that's because electromagnetic effects are simply not fully shielded in the way that's so often claimed. And I would suggest that we probably don't have any finite limits to space and time as actualized, whereas the Big Bang approach tends to just simply assume that there's finite limits to space and time. And also the Big Bang approach assumes only expansion redshift, increasing uniformly with distance. And I think that although redshift generally increases with distance due to non-expansion redshift, is also subject to substantial differences close to near compact objects in galaxies, as investigated and studied by Halton Arp and others, with, I think, very strong confirmation that there are redshift effects near compact objects and so forth that are not encompassed by a simple expansion redshift. And then I think that whereas the standard approach focuses on the creative impetus is being focused on the Big Bang event, and so to speak, everything almost deductively rising from that, that there's ongoing creative development evolution at all scales without limit. That's so. Next slide, please. So then the one can, you've no doubt everyone has seen a picture of the solar system, and most often such a picture is something like this, where you see all the different planets and planetary bodies and the asteroid belt and so forth. But and it's sort of like emptiness in between, and indeed scientists just simply presumed we have basically emptiness in between up until the late 1950s, when upon the Explorer 1 satellite that was with the instrument of Van Allen's in January 1958, with the first scientific instrument, was the discovery that there are plasmas in the space environment. And as we went on to do further experiments in the early space era from 1958 through the 70s, it was discovered that everywhere you sample, you've got a plasma medium from the ionosphere on out to the sun and throughout the interplanetary medium and beyond. So the standard view of the solar system, which neglects that space environment and presumes that at any significant scale that any electromagnetic effects are shielded out, and that there's no particular role for electromagnetism at large scale. And so insofar as there's any space environment, it can be ignored. That's often the standard view. And further, in modern astrophysics, if you read the journals, almost any plasma is treated merely a gas. So next slide, please. So in terms of primary natural systems, one can characterize, in terms of primary naturally occurring systems. Now, in terms of states of matter, there's more than 30 different states of matter, very exotic states of matter and so forth. But in terms of naturally occurring states of matter, there's basically three fundamental types. There's either condensed matter solids, which are described by a certain formalism for condensed matter. There are liquids and neutral gases, which can be described by the Navier-Stokes equations and for formalism for fluid systems. And then there are plasmas that we need to characterize using the Maxwell-Boltzmann formalism and the plasma formalism. These are electromagnetic systems, and in certain approximations, they can be treated as a sort of effectively gas-like or fluid-like descriptions of plasmas, but that doesn't mean that one can do that. It depends on a particular case-by-case basis. But the standard Big Bang paradigm, for the most part, looks at the world and looks at only the first two fundamental types of systems, treats them all in those two types, and simply sets aside and neglects plasma effects. Next slide. So by definition, plasmas are an interactive mix of charged particles, neutrals, and fields that exhibit collective effects. And these charged particles are subject to long-range collective Coulomb interactions or electromagnetic interactions with many distant encounters. And the electrostatic force drops off the distance, 1/r², dropping off, but nevertheless, the combined effect of all charged particles might not decay because the interacting volume increases as r³. So magnetic effects are often global, with their connections reaching to galactic scale and beyond. In fact, we now have direct evidence from measurement of galactic scale magnetic fields. And this is documented in detail in the wonderful book by Goldblatt and Potes, Principles of Minute Hydrodynamics. They also talk about the problems with the standard view, and very much the way I'm critiquing it here. And one can say that everything evolves, yet the whole itself does not evolve, fulfilling the cosmological principle for both space and time, that everywhere is, so to speak, the same in terms of some average, and everything evolves, but you can nevertheless have tremendous inhomogeneity and variety, but it depends on the particular scale. Next slide. So the standard view with a focus on gravity, it's focused on neutral bodies and gravity. And I'm saying the approximation of plasmas as fully shielded ionized gas, fully shielded at all times, is common by references by astronomers in, say, literature, especially in the literature related to cosmology, to gas and never to plasmas. The word plasmas hardly ever appears in these discussions. But space physics research throughout the solar system, where we have direct in situ measurement and can do quantitative testing with quantitative models and back and forth between that modeling and the direct measurements over the last 60 years, that this approximation that you can ignore, treat plasma is always merely a gas, and that you can ignore its unique effects of its unique electrodynamic effects, that approximation is invalid everywhere direct measurements have been made. The result is, and we have to always attend to the effects of like magnetic effects, the magnetic field and plasma effects. There are two long-range forces, gravity and electromagnetism. Next slide. So we look out from the Earth and we look to the sun, but you never, you might occasionally see the aurora borealis, but for the most part, the plasmas are not visible. They don't scatter in the visible radiation. You look out and it looks like there's emptiness. And this is why we had this preconception that, so to speak, space is empty. It's called space. That's, almost means emptiness, right? But space is not empty. It's just full of, but mind you, it's very tenuous. It's very low density. It's like a million times less dense than what's right in front of me, but it's still something. And mind you, when you consider that the scale is so large, the total energy involved can be substantial. For example, in the near Earth vicinity, we have a magnetosphere, and upon a particular, say, solar storm that interacts with the system, you can have 1 to a few million ampere currents involved. You can have potentials of 15 to 30 kilovolts and more over a 10 to 30 times the Earth radius scale, and the total energy involved can be like that of many terrestrial Earth storms at any given time, even though at any particular local place, the amount of energy involved is very small. So even though it's exceeding low density and things are very spread out, but because of the very scale of the system, you can have substantial energies. And further, the interactive scales are very different. We're used to, in the terrestrial environment, that the movement of airflow will be maybe a few meters per second, or maybe at most a kilometer per second. But in this domain, like in the low density plasmas, the energetic electrons can go from pole to pole and back in less than 1 second for 40 kilovolts. The time scale to go from an interaction at the front of the magnetosphere to the deeper tail can be not more than just a few minutes. The aurora borealis, the fluctuations of the discrete aurora and the patterns there, if you've seen it in person, you realize that those patterns can change dramatically on a few second time scale. And this is because of the very rapid interaction of the fast flowing electrons and the fast, very rapid electrodynamic effects, which are often, for example, alpha velocities are 100 to 500 kilometers per second. So these are very large systems, but the associated propagation speeds are very high. Next slide, please. And yes, we look out, for the most part, you don't see anything visible, but it's something's necessary, nevertheless is there. And when we take direct measurements of the near to the sun in ultraviolet, you get these dramatic loops of plasmas flowing along the magnetic field, and they're really beautiful. But to the naked eye, they're typically invisible. Except sometimes you'll see the corona of the sun if you have a solar eclipse, and we use artificial eclipses from satellite to be able to take measurements like this. And when those measurements are made, as you can see in this example, that there's very dramatic plasma effects, and these plasma effects continue on out throughout the solar system via the solar wind and interact with all the planets. And every planetary obstacle sets up a magnetosphere, an interactive region. And this kind of process is going on throughout the universe, not just in the solar system. Next slide, please. So what are the characteristics of plasmas? They're multi-scale, there's filamentation, there's directionality, there's conductivity, there's interactivity, and they're everywhere. In terms of the sources that we look, when we look out and see these, the light coming from different sources throughout the universe, the light being emitted by particular stars and so forth. Well, those sources are almost essentially always plasma-based sources. In terms of the visible, as we look out and the visible universe is 99+% plasma. When you go, say, to the immediate, say, particular planetary bodies and regions where you have, say, high density where you can neutralize the plasma effects, then yeah, then those aren't necessarily plasma effects. Say compact objects, that's a different type of physics. But for the most part, the visible universe is a plasma universe. Next slide. So, and they're multi-scale. They're going from exceeding low temperature to exceedingly high temperature, from very low number density to very high number density. It's so to speak a fourth state of matter: solids, liquids, gases, plasmas, and they and what we're focused on with the space environment typically are very low density and relatively high temperatures, and that have these characteristics of highly interactive and the other characteristics I've just described. Anyway, they're multi-scale of all different types, and so that's part of the problem. They're often very complex to understand these systems, and it's and that's why they tend to be neglected, because they are complex. It's so much easier to do models in astrophysics, and especially in cosmology, if you don't have to worry about plasmas. There's a strong motivation to not bother with it because they're so difficult. Next slide. Next slide, please. Yeah, so here's examples of filamentation by virtue of aurora, which you may have seen or may not have seen in person, but if you have the chance to see them in person, I recommend it. They're wonderful and they're highly variable. It's like a wonderful light show. Next slide, please. And the directionality, lightning is a plasma phenomena, and they're highly directional, and that's another feature. Next slide. Next slide. And to conduct electricity. This is the Z machine in Albuquerque for studying highly high energy density systems. So just it's a dramatic illustration of electrical effects. Next slide, please. And the interactivity I've mentioned already about energetic electrons, flowing along magnetic field lines from pole to pole and do so back and forth in less than 1 second. And the solar wind as it flows by the Earth's outer boundary, the magnetospheric boundary, is flowing at some 50 to several hundred kilometers per second. Well, imagine something going by you at a few hundred, say, miles per second. That's really going fast. Next slide. So what in this conception, what is the future of astronomy and cosmology? Well, I think there's a tremendous future, and we just barely started, that we need to incorporate both gravity and electromagnetism in plasmas. Gravity sets the stage, but very much of the dynamics often is associated with plasma effects in some way or other. And in a summary of, say, contemporary theoretical physics, with full attention to the implications of new results in quantum physics, Formello states that space and time appear not to be fundamental concepts as usually presumed, that they emerge ultimately from quanta of some kind. So they're arguably derivative, not primary, as presupposed in assuming the Einsteinian framework alone. New multi-scale systems understandings are needed, and the field of plasma astrophysics has now become quite well established in the last 20, 25 years, in several books, many hundreds of excellent publications, but the impact on cosmology is quite unknown. Next slide. So you might say, well, how many models of the universe are there? Well, there's arguably, from what I've seen at least on the order of 100+ models. There's at least, say, a couple dozen somewhat viable models, and there have been traditionally in the last 30, 40, 50 years, 3 viable models, somewhat viable models. The Big Bang model, which was pretty viable, more or less, up until around 2005 or so. The quasi-steady state model, which I think still is somewhat viable. Hoyle, Narlicker, and others promoted that. It was presumed to be falsified by some results back in the 80s and 90s, but I think that's not the case. And a plasma approach to cosmology, as encouraged by a number of scholars, Eric Lerner among others. And right now, that's my inclination, some plasma-oriented cosmology. Anyway, I think a creative cosmology that is data-driven, that's what I support, which you need to address both effects of gravity and electromagnetism. Anyway, common features of all these models, insofar as plasma effects are in the standard Big Bang model in the early stage near the Big Bang event, then effectively you also have creativity, creation, physical evolution, the importance of plasmas in some way, and gravitation is associated with all the existing models. Next slide. So nevertheless, there's been, but with respect to the Big Bang approach, there's been many eminent scientists have rejected the standard Big Bang research program. The jury is still out, and I think there's many out there that say that's still the case. There's a few names, and there were 210 co-signers of cosmology statement expressing that back in 2004, and there's been several conferences on alternative approaches. So I think And I think the new results of JWST, the James Webb Space Telescope, have newly opened this discussion even further. Next slide. And in that, in a paper of 2004, a paper Bucking the Big Bang was published, in which it was stated that the Big Bang theory can boast of no quantitative prediction that has subsequently been validated by observations. The point being that there's a distinction between prediction and post-diction, even though in practice, almost always post-dictions are described as predictions. But if you make the distinction and insist that, well, a proper prediction needs to be where you have made the prediction prior to the measurement, and then the measurement is done to test whether or not, if you are, say, insist on that kind of distinction, then it's arguably the case, it's very difficult to find a case where the Big Bang Theory has done a genuine prediction. In fact, I actually don't know of a specific case. And also the troubling thing about the Big Bang program has been the growing number of hypothetical entities of which none has ever been observed. Dark matter, which avoids contradictory predictions for the a fundamental assumption about the Einsteinian approach. A dark energy hypothesis which avoids contradictory 8 billion year age for the universe in order to sort of enable it to be a larger age so as to avoid contradiction with evidence, and the inflation hypothesis enabling a smooth isotropic cosmic background radiation. But there's alternatives to the Big Bang that can basically fit a high percentage of the observations, and some of the alternatives actually have done predictions in advance of the measurement. Next slide. So an example of this is the Eric Lerner has this galactic origin of light elements, GOLE or goal hypothesis versus the Big Bang. And he documents a series of particular data sets and predictions that I've listed here in this slide based upon Eric's work. And he gives a confirmation year for the goal hypothesis and also confirmation year for the initial apparent confirmation for the specific quantifiable model within the Big Bang program. It's called lambda CDM, lambda cold dark matter. And so you have the particular year of that initial apparent confirmation, but then later on, it's been contradicted by results. And then certain yet later specific falsification of them with measured results getting well beyond the error bars that are allowed and normally allowed. Next slide, please. So an example of this is Riccardo Scarpa, Italian astronomer working with Eric Lerner, made a specific predictions in a paper submitted in April 25th of this year, in advance of James Webb Space Telescope measurements that would then become available starting in midsummer. Among those predictions is that they predicted fully formed galaxies as far back as one can observe with JWST. This is opposite what the Big Bang approach suggests, that there's an evolution of galaxies, and at the very earliest time, there should be no fully formed galaxies. They should be only the rudimentary elements of galaxies and only gradually emerging with time. Next slide, please. But when the actual data came in, here's a particular portion of the JWST deep field, and within this are some examples of fully formed galaxies, and some of these are inferred to be of exceeding distance, not very much after the nominal Big Bang event, but such that the standard model would not at all predicts such fully formed galaxies. Next slide. And then along with that, that at the same time, there's been multiple observations that have been ever more problematic for the standard model. Here's an example of measurements of helium with local stars. And on the horizontal axis is Z, the redshift, and a very low redshift that associates with very local stars, relatively local distance cosmologically. And the Big Bang hypothesis, where you have the initial Big Bang event, which would create a anomaly on the order of 24% helium, that would be a baseline. It would, no matter where you look, you should have at least 24% helium on average. But then when you look at local stars, it's dropping off where it essentially practically goes to zero. This is directly in contradiction with the standard model. Next slide, please. And then another thing, even more dramatically, Ricardo Scarpa, Eric Lerner, and others have worked with surface brightness data going back for the last 20 years, and especially utilized Hubble measurements as part of that, and now have looked at some of the most recent JWST results, which are continuing to line up with their prior results. So the Big Bang, the lambda CDM model, is the predictions are given by the red line of the log of surface brightness versus redshift. But the no expansion model of Ricardo Scarpa and Eric Lerner fits the measurements exceedingly well, as you can see in this plot. So this is a dramatic case of a difference between the standard Big Bang model and actual data results, and there's no explanation given for that I'm aware of for that large divergence. It's just so far just been ignored. Next slide, please. So there's concerns of methodology. There's a tendency in the Big Bang research program to focus on confirmation versus falsification. In fact, I rarely see the word falsification mentioned. Increase in adjustable parameters seems to be allowed without limit, and this undercuts falsification. Some core assumptions, like assumptions about what the basic measurement parameter of redshift is, presuming that it's expansion redshift, sometimes gets built into the very data analysis. And there's very little research investment in alternatives. For example, there's a specific quantitative model of a plasma redshift that has been introduced by Ari Brynjolfsson, a Danish physicist, very quantifiable, very testable, and there's no effort to test it, and yet it's testable. It can be, there are ways to do that. And doubt and dissent are often discouraged. In fact, it's come to my attention that within the past 15 plus years, there's been now a systematic effort among some major publications that if any submitted manuscript questions the Big Bang research program, that it will not get published. So this is not helpful for the progress of science. So then I think I'll leave it with that and turn over to Matt for maybe some further comments about methodology and philosophical issues, etc. Thank you.
Thank you so much, Tim. Fascinating rundown of the state of the art in cosmology, both new observations and just showing us this evidence from some of Michael Lerner and his colleagues' alternative proposals, which are fitting some of the data better. As a philosopher, I am fascinated by this debate about the Big Bang for methodological reasons, but I think also when we understand science in its historical context, it becomes very clear that while I wouldn't want to question, the motivations of physicists and astronomers who are engaged in this research, clearly they want to know the truth and they're doing their best to ascertain it. But in an institutional context, big science, quote unquote, is always going to need funding. The James Webb Space Telescope costs billions of dollars, right? And the research program that has built up around the Big Bang model, or it's really a meta model that contains multiple models kind of stacked on top of each other, right? There's a sort of tendency for the scientific establishment to get locked into the model because they want to secure further funding. And a lot of this funding is public funding from government agencies. And so there's a need for physicists, when they popularize these findings, to generate a lot of excitement among the general public that, we're on the verge of discovering, the origin of the universe and so on. And so as science gets popularized, because scientists want to secure more funding, science can sometimes shift into myth. Cosmology, from my perspective, is one of the branches of metaphysics. And in order to bring it more into science, which I encourage, it needs to be more data-driven, as you've been suggesting, Tim. The problem with cosmology is that we have precious few observations and measurements to go on, right? And the tendency, therefore, has been for astronomers and astrophysicists to let the mathematics guide them. There's a pursuit of mathematical unity with very few anchors in empirical reality, such that the sorts of models that are produced are of very low significance. As I see, I was just about to mention Michael Disney. Gary Herstein just dropped his name into the chat. Michael Disney has a wonderful article from almost 15 years ago called Modern Cosmology, Science or Folktale. And he points out that cosmology, currently the standard Big Bang model in cosmology, has a formally negative significance. And by that, he means that the difference between the number of measurements made and the number of free parameters introduced to fit them, the sort of free parameters as in the mathematical fudges, that this negative significance must remain, in other words, there's more free parameters to change than there is data to anchor those free parameters. So we would expect that a healthy research program would have a positive significance. In other words, it's making predictions, not postdictions, where when new observations are made, you just go back to the equations and tinker with them so that it fits. This approach to physical cosmology has much in common with the old geocentric model of the solar system, Ptolemy's model of the solar system with its various epicycles and deferents. Remember, if you put the Earth at the center to understand the retrograde motion of planets, Ptolemy devised an elaborate series of circles upon circles. It's quite a beautiful model, actually, and was highly predictive. It's just that it's factually wrong. Modern cosmology is, in a similar way, adding the equivalent of epicycles and deference to the standard model, with such things like dark matter to explain the observed rotational velocity of galaxies, or the accelerating expansion of the universe is accounted for with dark energy. Now, the problem with all of this is that it's so easy to confuse fact and theory. As Whitehead points out in the early pages of Process and Reality, he says the history of thought shows that false interpretations of observed facts enter into the records of their observation. Thus, both theory and received notions as to fact are in doubt. And so you see this sort of thing, this confusion between theory and observation all the time. A famous physicist, Sabine Hassenfelder, in an article published recently about the James Webb Space Telescope and Big Bang cosmology, she makes this mistake when she refers to the redshift of distant galaxies as proof of expansion, when actually to interpret the redshift of distant galaxies as expansion is just that. It's a theoretical interpretation. It's not an observation, right? And so we need to keep, Whitehead's warning in mind here about false interpretations of observed facts entering into the records of their observations. Let's see what else I want to add here. I think I'll shift over to some more philosophical comments about cosmology as I understand it from a process philosophical perspective, taking Whitehead's criticism of the bifurcation of nature seriously. Let me share my screen. I want to read a line from Process and Reality here. Everyone can see this page 170. Yep. So, Whitehead reminds us in the midst of a discussion about different forms of perception, presentational immediacy, causal efficacy, and symbolic reference, that all scientific measurements occur in presentational immediacy, right? And he says that every statement about the geometrical relationships of physical bodies in the world is ultimately referable to certain definite human bodies as origins of reference. A traveler who has lost his way should not ask, "Where am I?" What he really means to know, what he really wants to know is, where are the other places? He has got his own body, but he has lost them. And I mention this quote because there's a tendency in contemporary modern science after Galileo severed the so-called primary characteristics of the measurable quantities of external nature from the so-called secondary characteristics of the inner life and experience of organisms. There's a tendency to absent ourselves and to imagine that we have a view from nowhere on the universe. And the standard model of cosmology, in absenting ourselves, our embodied consciousness and perspective, attempts to take what we learn from particle physics, where we can actually do experiments on Earth about learning about the microcosm, right? Slamming particles together, and it tries to connect that to the macrocosm. And the Big Bang research program allows this sort of a connection, because the idea is that at one time, roughly 14 billion years ago, the universe was very small. And so observations of the quantum realm and particle accelerators can thereby be tied to our observations of the macrocosm, through cosmic microwave background radiation and so on. Now, the problem is this leaves out the mesoscale. And one of the things that interests me very much about Whitehead's process approach and the general process approach, whether it's coming out of Bergson or others, is that human experience needs to be taken seriously again. The mesoscale, the embodied middle, right? Our human consciousness needs to be remembered, and all of our science needs to be brought back into proportion with the organism that we are and the type of experience that we have. Otherwise, we run the risk of imagining that we could understand the universe from the outside, right? We are in the universe, and I think Whitehead allows us to check this tendency, going back to Galileo, to mathematize the world. There's much that can be learned from mathematics and from measurement, but this leaves out the interior of the world, right? Max Planck, brilliant physicist, championed the mathematization of nature. Where he said, I quote, "The increasing distance of the physical world picture from the world of the senses means nothing but that a progressive approach to the real is being accomplished." So in other words, the more we learn to ignore our embodied sensory experience of the world, the more we can mathematize our models of the universe, the more we approach the real, right? This is Planck's view. Whitehead, in contrast, says that the divergence of formula about nature from the appearance of nature has robbed the formula of any explanatory character, right? Because for Whitehead, a valid explanation would include our embodied experience, not excise our experience from the world. So I think we need to bring our understanding of the cosmos at large back into conversation with our direct human experience and consciousness. And I'll leave you with this couple of sentences from Whitehead's Adventures of Ideas. You should be able to see this highlighted here, where he says, "On a moonless night, the faintly luminous stretch of the sky, which is the Milky Way, is an appearance of the contemporary world. Namely, it is a great region within the receptacle of that world as it appears. But the reality whose functioning issues in that appearance is a flux of light energy traveling through the utmost depths of space and, to our imaginations, through illimitable time. Beyond that Milky Way, as it stands in sight, at a finite, ill-defined distance, a barrier separating us from the contemporary space beyond. Does that remote activity of the transference of light energy still persist as a contemporary fact? Perhaps the occasions whose interconnections constitute that distant region have changed the ordering of their goings-on. Stars flare out in a few days, and in a few years their light has died. The appearance of the contemporary regions has its truth relations to the past and its truth relations to contemporary reality. These latter truth relations can only be estimated by an imaginative leap, which has as its basis for justification the truth relations to the past and our experience of the stability of the types of order involved. Perhaps the mutual immanence of occasions, although the antecedents and the consequence, the past, the present, and the future, still hold equally for physical and mental poles, yet the relations of the mental poles to each other are not subject to the same laws of perspective as are those of the physical poles. Measurable time and measurable space are then irrelevant to their mutual connections. Thus, in respect to some types of appearance, there may be an element of immediacy in its relations to the mental side of the contemporary world. Other types of appearance, such as the located sensa and sense perception, may depend on the time and space which express the perspective arising and the mutual immanence of the physical poles. If such be the case, some types of appearance will have a more direct relation than others to contemporary reality. Now, I read this because I think it relates to Tim's point about the space-time metric being derivative from quantum process. And what Whitehead is suggesting here is that while in the physical pole, the space-time metric is important and relevant, and that in that physical pole, when we consider it abstractly and put the mental pole aside, that measurement of the large-scale structure of the universe becomes possible. However, when we include the mental pole, it becomes clear that in the depths of our own experience, we have some immediate relationship to the expanses of the cosmos. And through what he calls an imaginative leap, through our own imagination and intuition, I think what Whitehead is suggesting is that we can connect with the causal processes that are going on in the broader universe, in some sense that there's a way in which, though in space-time metrical terms, they are very far away in space and time, in the unison of becoming of the cosmos as a whole, all of it is right here with us, mutually immanent in our own experience. And so while we can't necessarily draw scientific truth from this imaginative, intuitive form of experience, from Whitehead's point of view, science in its measurements of the universe only gives us half the picture, right? To understand the cosmos as a living process, as a creative process, we can turn inward into the depths of our own experience and gain insight there as well. So it's an invitation to the non-scientists among us to not cease from their own cosmological dreams and speculations, though always do so in conversation with science, right? So I'll stop there, and I will invite Tim initially if he has anything to respond to in what I've shared, and then we'll open it up.
Well, thank you, Matt. I really like all of your comments, including the great quotes from Whitehead and the distinction important for, say, at one hand, our temptation to want to see as if the eye of God, to be able to see it as a view from nowhere, and at the same time, the importance of the possibilities of measurement, of the foundations of how we access and know the world and elements of consciousness, and so of our present reality. And so those distinctions are critical, I think, and I've also developed those in some length in my book, Untying the Gordian Knot, which I recommend to people, very consonant with your comments. And so I've so with that, I have nothing further right now to note. Let's go on with further Q&A or whatever. Thank you.
Maybe, John Cobb, you were one who raised this question about all of the Big Bang and how everybody takes it for granted. And maybe give you a chance to see what you've learned from this conversation.
Well, I've learned something that I knew I would learn, namely that the situation is vastly more complicated than any way I had been able to describe it. But the complications only reinforce my suspicion that those who are holding on to the Big Bang theory are not really functioning as good scientists. Their motives are something other than that. I don't mean that, and I'm not saying consciously so, but they are, you can't have an experience of finding that things don't work out the way you expect them to based on your theory again and again and again, and still hold on to the theory without something more than a scientific treatment of it as a theory. It becomes a dogma. And of course, we know all about dogmas in other fields, but it troubles me that scientists seem no more free of dogmatic thinking than others. We'd like to think that the study of science frees you from dogma, opens you always to the evidence. I mean, I've been disillusioned on that point for some time, but I appreciate this presentation because it makes so clear. And I do believe that the interest in evidence has not gone out of the scientific community. That it won't be too long before scientists say, well, we really worked on that theory a long time, but we can't find any evidence for it. And there does seem to be evidence for some other theories. We'll begin to investigate them. So these are simply naive comments from an outsider. I appreciate what has been done here very much.